Hello, I'm Ken Mitchell. I'm excited to share with you the following slides on AMD Ryzen processors, which power today's game consoles and PCs. Let's begin. Today's agenda includes abstract, speaker biography, products, microarchitecture, data flow, best practices, and optimizations. Join AMD for an introduction to the AMD Ryzen family of processors which power today's game consoles and PCs. Learn about Ryzen products, dive into instruction sets, cache hierarchies, resource sharing, and simultaneous multithreading. Discover profiling tools and techniques. Gain insight into optimization opportunities and lessons learned with examples in C, C++, assembly, and hardware performance monitoring counters. I'm a principal member of technical staff in the AMD game engineering team, focusing on helping game developers utilize AMD processors efficiently. Recently, I worked on Windows 11, 3D Mark, Unreal Engine, and Resident Evil Village. Previously, I worked in SoC modeling and benchmark development teams. My work email address has been kenneth.mitchell@amd.com since 2005. Products. New AMD Ryzen mobile processors bring together Zen 3 Core with AMD RDNA 2 architecture-based integrated graphics to create a computing powerhouse delivering revolutionary gaming performance and battery life for laptops. Many games running on integrated graphics benefit from the additional memory bandwidth provided by DDR5 and LPDDR5. The AMD Ryzen 7 5800X3D is the first desktop processor with stacked L3 cache, delivering unmatched 96 megabytes of L3 cache paired with incredibly fast cores to create the world's fastest gaming desktop processor. AMD Ryzen 5000 G series desktop processors include AMD Vega architecture-based integrated graphics. Professional content creators can now leverage the fastest, most versatile workstation processor ever created, with unmatched core counts for multi-threaded workloads that rival competing dual-socket solutions, and high-frequency single-threaded performance for lightly threaded tasks. This unique full-spectrum compute capability enables reduced render times, more creative iterations, faster simulation solving, quick rebuilds, and smooth interactivity with 3D assets. Microarchitecture. Advances in Zen 3 microarchitecture include a 19% IPC improvement, a unified 8-core CCD with 32 megabytes of L3 cache per CCD, an improved load store unit with up to 3 loads per cycle and up to 2 stores per cycle, wider floating point and integer execution units with an additional floating point pipe for float to int conversion and another for store, and an additional integer pipe for branch. Zen 3 also improved SMT fairness. High-performance cores have gaps in utilization which may be filled by additional hardware threads. This is simultaneous multithreading. Although each hardware thread has its own program counter and architectural register set, they share core resources. Consequently, there may be architecture-specific bandwidth and latency trade-offs. Skilled developers may apply knowledge of these trade-offs while optimizing for performance. Zen 3 supports two-way SMT and may run in either single-thread or dual-thread mode. Program thread select occurs during branch prediction and is typically done using round-robin scheduling. Some resources within the core may be shared while in dual-thread mode. The core is in dual-thread mode while both its logical processors are executing program threads. If either of the core's logical processors execute the operating system's idle thread, the core may return to single-thread mode. Disabling SMT and BIOS menu options will reduce the number of logical processors in the system and limit the core to operate only in single-thread mode. Let us review core resource sharing categories and definitions. Competitively shared, resource entries are assigned on demand. A thread may use all resource entries. Watermarked, resource entries are assigned on demand. When in two-threaded mode, a thread may not use more resource entries than are specified by a watermark threshold. Statically partitioned, resource entries are partitioned when entering two-threaded mode. A thread may not use more resource entries than are available in its partition. Resource entries are unpartitioned when exiting two-threaded mode. Caches and TLBs are competitively shared for both Zen 2 and Zen 3. For Zen 3, the integer scheduler, integer register file, and load queue have changed from competitively shared to watermarked. These changes improved SMT fairness. Zen 2 increased the L3 cache size and increased the micro-op cache size. Zen 3 further increased the L3 cache size, which is great for gaming. Zen 3 added vectorize AES and vectorize carryless multiply instructions often used in cryptography. Additionally, parallel bits extract and parallel bits deposit instruction latencies have been reduced to 3 cycles. Please note Zen 3 does not support AVX512 or AMX instructions. Software prefetch instructions, by definition, load a cache line from the specified memory address into the data cache level specified by the locality reference hint T0, T1, T2, or NTA. This instruction is implementation dependent. Prefetch fill and evict policies may differ for other processors. Policies for Zen 1, Zen 2, and Zen 3 are shown. Prefetch levels T0, T1, and T2 are implemented in hardware identically. All fill into the L1 cache. However, prefetch level NTA lines are marked for quicker eviction from the L2, and when eventually evicted from the L2, are not inserted into the L3. If a memory fault is detected, the instruction is treated as a no-op. Use software prefetch instructions on linked data structures experiencing cache misses. Use NTA on use once data. For workloads that miss in the L1 or L2 caches, software performance may improve if data structures are designed such that the data access patterns match one of these listed behaviors. The L1 stream and stride prefetchers are most noteworthy in my opinion. Stream prefetchers may fetch additional sequential lines in ascending or descending order. Stride prefetchers may fetch additional lines when each access is a constant distance from the previous. The L2 cache also has a stream prefetcher. Additionally, there is an up-down prefetcher which may fetch the next or previous line. Some AMD products have cores which are faster than other cores. AMD calls this feature preferred core. The system bias describes the CPPC highest performance ranking for each logical processor. The Windows kernel creates a performance scheduling class ranking based on this information and uses it during scheduling. Microsoft calls this feature favored core. For some AMD products, the fastest logical processor number may be different on another serial number part for the same OPN. Logical processor 0 may not be the fastest core. CCD 0 may not contain the fastest core. For these reasons, I typically recommend not setting process affinity or thread affinity masks, which may interfere with favored core scheduling. Data flow. This slide shows an abstract diagram of an AMD Ryzen 7 6800U mobile processor. Imagine data moving from the DRAM on the far right through the data fabric, caches, and cores on the left. Each unified memory controller manages 32 bits of DRAM. A DIMM is composed of two 32-bit channels. DDR5 4800 and LPDDR5 6400 are supported. Note this is a single monolithic die SoC design where the orange-colored complex L3 cache connects to the blue-colored data fabric at 32 bytes per cycle read and 32 bytes per cycle write. Here we have an abstract diagram of an AMD Ryzen 9 5950X desktop processor. This is a chiplet design where each core complex die has a unified 8-core cluster with a massive 32 megabyte L3 cache. This change greatly improved cache hit rate and reduced data fabric contention for some applications. Finally, this slide shows an abstract diagram of an AMD Ryzen Threadripper Pro 5995WX 64-core 128 logical processor. This product has 8 channels of memory and 128 PCIe lanes. You can add many GPUs and NVMe drives to this beast. This topology with up to 8 CCDs is so large that I've shown it in quadrants for simplicity. Note each quadrant looks similar to the mainstream desktop product design, but with a larger I/O die for additional memory channels and PCIe lanes. Best practices. Build times may be reduced significantly by optimizing your system configuration. Based on my experience, I recommend high core count processors such as Threadripper with at least 2 gigabytes of memory per logical processor. The 64-core 128 logical processor Threadripper used in this example has 256 gigabytes of system memory. Less memory may result in compile errors unless the Windows paging file is increased, or unless the Windows paging file size is increased, or build script modified to use less logical processors. Build times are also sensitive to compiler version and Windows virus and threat protection settings. Use the latest compiler in Windows SDK. Get the latest build and link time improvements. Rebuilding UE4 is much faster on Visual Studio 2022 and 2019 compared to Visual Studio 2017. Some developers have experienced larger benefits than those shown. Ensure you're using the latest C runtime optimizations, especially for memcopy and memset. Windows Defender scans can greatly slow down some workflows. Windows 11 enabled the Windows Defender sandbox feature by default, which greatly improved security but also increased file copy and file compress times. Add project folders to virus and threat protection settings exclusions for faster build times. This system showed a 20% reduction in build time by adding folder exclusions. Warning, this recommendation is for personal development systems only and not continuous integration and continuous deployment systems. Prefer shipping configuration builds for CPU profiling. Debug and development configuration builds may greatly reduce performance. Stats collection may cause cache pollution. Logging may create serialization points. Debug builds may disable multi-threading optimizations. While investigating open issues, developers may submit change requests which enable debug features on test and shipping configurations. Be sure to disable debug features before you ship. Disable anti-tamper while CPU profiling. Build a binary similar to shipping configuration, but without anti-tamper or anti-cheat, which may prevent CPU profiling tools from properly loading symbols. Audit content. Ask artists to recommend scenes of interest for profiling. For example, an indoor dungeon with heavy occlusion, an outdoor city, an outdoor forest with alpha transparency, large crowds, or a specific time of day. UE4 developers may find some performance issues simply by running map check, especially for issues related to actor shadows. Unity developers may enforce minimum standards using the asset postprocessor. Check stats before CPU profiling. If the scene far exceeds its draw budget or has many duplicate objects, especially duplicate physics objects, consider reporting the issue to its artist and profiling a different scene. Otherwise, you may risk profiling hot spots which may not be hot after the art issues are resolved. Test the cold shader cache first-time user experience. Be sure to clear the application shader cache if it has one. The end user will often not be running the same scene back-to-back as a developer might. The example shown clears the Microsoft, AMD, and NVIDIA shader caches. Reboot after running this script to clear any shaders still in system memory. Applications and games may vary configurations of shader caches on disk, yielding different results. Results may also vary based on GPU vendor and driver versions used. Optimizations. Today's topics include use the AMD core count sample, use modern sync APIs, avoid false sharing, prefer data access patterns matching the hardware prefetcher behaviors, use software prefetch instructions for linked data structures experiencing cache misses, align memcopy source and destination pointers, avoid penalties while mixing SSE and AVX instructions, support hybrid graphics, and use preferred video and audio codecs. Use the AMD core count sample. This advice is specific to AMD processors and is not general guidance for all processor vendors. Many applications show SMT benefits and use of all logical processors is recommended. However, games often suffer from SMT and cache contention on the main or render threads during gameplay. Creating the thread pool size based on physical core count rather than logical processor count may reduce this contention. Profile your game to determine the ideal thread count. Game initialization, including decompressing assets and compiling and warming shaders, may benefit from logical processors using SMT dual thread mode. However, gameplay may prefer physical core count using only SMT single thread mode. A core count detection code sample is available at gpuopen.com. We recommend using all logical processors for game initialization. However, our recommendation for gameplay thread pool size is to use the physical core count on systems with at least 8 Ryzen CPU cores. This is based on our experience and subject to change. We have seen some games improve frame rates by 5 to 10% thanks to this optimization. Actual results may vary. Profile your application for best performance. Use modern sync APIs. Some modern sync APIs, such as standard mutex, may leverage AMD's mwaitx instruction to efficiently wait on an address or timeout. Legacy sync APIs, such as wait for single object, may have additional syscall overhead. This microbenchmark shows significant performance improvement by using standard mutex rather than wait for single object. Core isolation memory integrity, otherwise known as virtualization-based security hypervisor protected code integrity, may have a significant performance impact. Windows 11 ships with this feature enabled by default to provide stronger protections against malware. User spin locks may consume OS thread scheduling resources unnecessarily since the OS scheduler may be unable to determine if it should yield to another program thread rather than spin. Consequently, user spin locks may starve other ready threads doing payload work. Moreover, user spin locks may consume a lot of power. For notebook users, this may drain battery life and reduce the power budget available to the GPU. Beware of user spin locks. Here's the source code for the main function used in the exclusive lock microbenchmark. Basically, it times how long it took all threads to execute the callback function. The code for the bad spin lock and its callback function are shown on this slide. Note the while loop does not include a pause instruction. Ouch! This spin loop may consume core resources in an overly aggressive manner while doing non-payload work and be very painful for older processors with less SMT fairness. This user spin lock has 3 improvements: test, then test and set, the pause instruction, and align the lock variable. These changes may greatly improve performance on older processors with less SMT fairness. For the current generation Threadripper, microbenchmark execution time was reduced by about 10% when compared to the bad user spin lock. Wait for single object with create mutex are shown in this example. These two APIs have been around for a long time. The wait for single object function checks the current state of the specified object. If the object state is non-signaled, the calling thread enters the wait state until the object is signaled, or the timeout interval elapses. Thus, wait for single object may not suffer from OS thread scheduling and core resource sharing issues caused by some bad user spin locks. Note this example requires some initialization in main. Better yet, standard mutex is even faster than wait for single object. This modern sync API is based on a slim reader-writer lock in Microsoft's implementation and can be verified using the Windows Performance Analyzer. In my testing, standard shared mutex and intercritical section also outperformed wait for single object. Finding and fixing false sharing issues may have great performance benefits. This microbenchmark showed its execution time reduced by 90% after optimization. For this example, each thread accesses a single thread data element within an array. Before the optimization, the array was compact, but unfortunately, different threads frequently modified the same cache line while using their thread data in the callback function. Simply padding each thread data using align as of the native cache line size resolved this issue. Prefer data access patterns matching hardware prefetcher behaviors, especially for streaming and Stride. The streaming hardware prefetcher uses a history of memory access patterns to fetch additional sequential lines in ascending or descending order. This simple example may trigger a streaming hardware prefetcher as it iterates the contiguous array. Similarly, iterating standard vector may also trigger this prefetcher. The Stride hardware prefetcher uses a memory access history of individual instructions to fetch additional lines when each access is a constant distance from the previous. 2 strides are detected in the code samples shown. Again, iterating standard vector may also trigger this prefetcher. However, the stream and Stride code snippets may not trigger a hardware prefetcher if they iterated instead using a linked data structure with nodes scattered randomly across memory. Use software prefetch instructions for linked data experiencing cache misses. In this example, performance improved over 60% using software prefetch optimizations. Results may vary significantly for systems with different cache sizes or different memory latencies. The NVIDIA Physics Kappa demo iterates a standard vector of pointers. Consequently, the stream and Stride hardware prefetchers are of little help due to the pointer chase. Before the optimization, many of the data accesses in the innermost loop miss the 4 MB last level cache of the AMD Ryzen 7 4700G. Since the convex class member data is not public, offset of keywords cannot be used, and thus literal offsets are shown. Although not illustrated in this example, additional performance may be possible by reordering the hot member data to occupy only 1 cache line rather than 4. Update the compiler for the latest memcopy, memset, and other C runtime optimizations. Memcopy behavior is undefined if the destination and source overlap. However, the compiler may generate rep move string instructions which have defined overlapping behavior. A LineAS64 may allow faster rep move string microcode. A LineAS4096 may reduce store-to-load conflicts. The processor uses linear address bits 0 through 11 to determine store-to-load forward eligibility. That's a tongue twister. PMC24 load store bad status to STLI other counts store-to-load conflicts where a load was unable to complete due to a non-forwardable conflict with an older store. Additionally, a LineAS4096 may benefit probe filtering on AMD Threadripper and EPYC processors. Finally, aligning to the bit floor clamped between 4 and 4096 bytes may provide a good balance of cache hits and alignment. There is a significant penalty for mixing SSE and AVX instructions when the upper 128 bits of the YMM registers contain non-zero data. Transitioning in either direction will cause a microfault to spill or fill the upper 128 bits of all YMM registers. There will be an approximate 100 cycle penalty to signal and handle this fault. To avoid this penalty, a V0 upper or V0 all instruction should be used to clear the upper 128 bits of all YMM registers when transitioning from AVX code to SSE or unknown code. In this example benchmark, execution time was reduced by 60% after a V0 upper optimization. Use PMCE, floating point dispatch faults greater than 0, to find code which may be missing V0 upper or V0 all instructions during AVX to SSE and SSE to AVX transitions. Here are 3 simple optimizations which may mitigate this performance issue. First, use the ARC AVX compiler flag. AVX is supported by approximately 94% of users according to the January 2022 Steam Hardware and Software Survey. However, this may not be a viable option for software with very old SSE to minimum hardware requirements. Second, return a M256 value using pass by reference in the function parameter list rather than the function return type. And third, use force inline on the function definition. Any of these changes may allow compiler optimizations to reduce floating point dispatch faults. Here's an excellent example of the floating point dispatch faults issue encountered by Mikkel in his Mesh to SDF benchmark. Both the before and after optimization examples are compiled using the default ARC SSE2 flag. Before the optimization, the function return type is a M256 value. After the optimization, the M256 value is returned using pass by reference in the function parameter list. Using AMD Microprof, we can quickly find the hot line of source code and its assembly code. In this example, the rightmost column is the floating point dispatch faults per 1,000 cycles, which is greater than 0. Looking at the assembly code, we can see there is a variable blend pack single precision AVX instruction, which is soon followed by a move align pack single precision SSE instruction where the upper 128 bits have not been cleared by a V0 upper or V0 all instruction. This needs optimization. After the optimization, the M256 value is returned using pass by reference in the function parameter list. Using AMD Microprof again, we can find the same line of code and its assembly code. We can quickly observe floating point dispatch faults per 1,000 cycles is 0. Yay! The compiler has inserted a V0 upper instruction between the variable blend pack single precision AVX instruction and the move align pack single precision SSE instruction. This performance issue is resolved. Additional considerations may be necessary to ensure the expected GPU is utilized in hybrid graphics platforms. The Windows 10 Spring 2018 update added enum adapter by GPU preference. Use DXGI GPU preference high performance for game applications. The user may change preferences per application in Windows graphics settings. Prefer H.264 video and AAC audio codecs as recommended by the Unreal Engine Electra plugin. Hardware-accelerated codecs may increase hours of battery life and reduce CPU work. Please note the WMV3 codec is not hardware-accelerated in recent products such as Radeon RX 6500 XT, Radeon RX 6400, and AMD Ryzen 6000 series mobile processors. If you are using WMV3 content, please replace it with H.264 content, which may provide a better user experience. Developer.amd.com has software optimization guides for Zen 2 and Zen 3. Discover your best graphics performance by using our open source effects, SDKs, tools, and tutorials at gpuopen.com. Design faster, render faster, iterate faster. I can't wait to see what you create.